Hello, everybody. Thank you for joining. We are going to wait a few minutes as people get here, but I am going to start with some introductions, and I would love to know where people are joining us from. So if you want to, on the right side of your screen, there's a little comment box. Just tell us where you're joining us from. And Patrick and I are both here in Boulder, Colorado. So just a little bit about us. Iron Core Labs is a data security platform. We focus on protecting sensitive data in cloud applications without sacrificing the ability to use that data. That is a very important part of what we do. And during the webinar today, there is going to be a lot of information. So if you have a question, we have an Ask a Question button. It's at the bottom of your screen right here. Click that. Add your question. We'll either be able to answer the question live while Patrick is talking, or we'll wait till the end. We have a Q&A planned at the end, and you can ask your questions. We have a poll. Feel free to also, if you have questions or comments, if there's a technical issue and you can't see the screen or something, it might be not just you. There could be other people who can't see too. So feel free to post in the comment section if anything like that happens. Hopefully not. All right, it looks like we have some people joining. Welcome, everybody. Spokane and Bozeman. Got an Erie, Colorado. That's just next door. Awesome. Well, I am going to go ahead and introduce Patrick. So Patrick is the CEO and co-founder of Iron Core Labs. He has more than 20 years of experience building successful teams and products and solving difficult problems in the enterprise software and security domains. And he's named investor in multiple patents on novel cryptography and a longtime advocate for privacy and security. And I'm really excited to hear this presentation that Patrick has put together today. So Patrick, go ahead and take it away.
Hey, thanks, Raya. All right, we have a lot of ground to cover in the next 35 minutes or so don't be scared. There's a lot to take from this, regardless of your level of understanding of AI and cryptography. There is something for everyone. So let's jump in. Intelligence. What does that mean? And what does it mean to be artificial? Honestly, there's no one answer. AI, like any other computer program, takes some inputs and it processes them and it generates outputs. It's just another set of tasks reduced to math and calculated. What's new and different with AI is that we understand what's happening inside the box much less than we do with other sorts of programs, because there are actually two phases involved. The first phase takes note of how things are associated with each other, and the second phase uses what was learned in the first phase to make conclusions about new inputs. And this is interesting to us because it seems very, very familiar. Our brains aren't just calculators, but are pattern matchers that can see and classify and draw connections between things. Only with AI, we have all kinds of terminology we like to throw around. The learned associations are stored in a model, and when it gets inputs and tries to understand them by using that model, it produces inferences, which is a fancy way of saying conclusions. And although we know exactly how AI works, we have a hard time predicting what it will do or understanding specifically why it gets something wrong when it does, sort of like our own brains, which we barely understand. And look, there is no AI brain. It's a pretty silly analogy, actually, for a bunch of fancy math and programming. But our brains learn better when there are understandable metaphors involved, and this one can be pretty handy, which is why I'm going to lean on it and use it today to help the concepts that I'm explaining stick. But it's also a dangerous metaphor because it leads to pundits sowing fear and of machines taking over and evil intelligence deciding that humans are unnecessary, or at least taking over all of our jobs and leaving most of us destitute. But look, this stuff isn't magic, but it's talked about like it is, which is why I want to start off by sprinkling in a bunch of much neglected context to compare the simple systems of AI to something that is much more powerful. AI runs on electricity, and it needs a lot of it for processing, for cooling, and so on. And while meaningful stats and figures are kind of hard to come by here, we know that training a large model costs millions of dollars in electricity, and more anecdotally, making inferences with large models on my computer absolutely burns up CPU and GPU time. By comparison, our brains also operate on electricity, Sort of. They work through a stream of electrical pulses like taps of Morse code, and they weigh about the same, that is, our brains weigh about the same as a MacBook Air, if you ignore the skull and everything else on the head. Running the human brain takes just 400 calories per day, about one blueberry muffin, regardless of how hard we work or how lazy we are. And in 30 seconds, the human brain processes more information than the Hubble telescope has in 30 years. Our human brains can hold around 200 exabytes of information, roughly equivalent to the entire digital content of today's world. That's 200 million terabytes, if that's a more familiar number for you, which is more storage than I could fit in my house if I stuffed it full of server hard drives. And we get so much more data. From our eyes alone, we get 100 billion signals every second, and that only accounts for 10% of what we see. The rest comes from our processing of those signals to recognize faces, interpret movements, identify danger, to build up a mental picture of everything around us in real time. So, if you want to compare AI to the human brain, there's really no contest. The human brain is way more impressive and way more capable. And besides vision, it has way more inputs. And besides interpreting inputs, it's also sending signals to our body, taking in signals from our body, monitoring and controlling all the systems therein. So while a computer can begin to recognize and label things in images and maybe associate words with ideas, we humans can synthesize entire experiences, piecing together 33 different senses, including a sense of balance, of acceleration, of where we are in space, time passing, appetite, smell, temperature, and so on. Our brains evaluate and retain way more information than any computer can even fathom. But there's one exception to our clear superiority here, and that's memory. Our memories mix together all of those senses, while AI memories are relatively shallow with limited understanding of specific inputs. But our memories are kind of curious things. They're liable to get rewritten by us and by others. We're prone to false memories of things that never even happened, formed only by suggestion. And we have no direct control over what memories we retain and which ones fade away. But fade away they do. These processes are out of our direct awareness and control, whereas computers can retain details as long as needed. And when we process information, we filter the heck out of it before we store it. We're quick to discard anything that seems uninteresting to us. So for example, if we look at this photo, it's likely we'll quickly process it and understand much of what's happening in it. But it's also likely that we'll only retain the major points and discard the rest. So we might remember that there's a guy about to drop into a swimming pool on a skateboard with a small crowd watching. And I don't know about you, but I probably had an impression that it's summer and maybe some sort of contest, and I certainly noticed that's in black and white. But I really have to study it more to remember much else. But an AI does not filter like that. It will take note of, and if it's trained in how to do so at least, remember how many people there are there. 17 by my count, and what the signs say, and how many tents there were, and so forth. Now, those might be unimportant details, certainly they are to me, but the AI produces these inferences, and if they're stored, the AI can later recall and use them however it needs to. So in thinking about these systems, it's useful to imagine the AI brain as having two parts. The first part is the model, which is that knowledge base and recognition center that makes decisions or inferences. This represents everything the AI learned when it went to school, so to speak, in that first phase of the AI lifecycle. It's like this side of the brain doesn't have anything in it beyond its childhood when it was in its learning phase. The right hemisphere we'll call the memory of the brain, and in an AI system, this memory is anything that you expressly want the system to remember for later use. This is all of the important things that it's run across since its childhood, since the AI model was trained. So information from new inputs after the model was built, like perhaps that skateboarding picture, get retained in this memory. And this memory is what people mean when they talk about vector embeddings. The term vector embeddings is a reference to the storage format for these AI memories. And that memory is then stored in various ways, sometimes just in volatile RAM, sometimes in these index files, or more recently, in getting more popular every day, in vector databases. And going forward, I think we'll see vector databases become the preferred way to manage persisting inferences because of the capabilities that they offer. So to understand these better and maybe more intuitively, let's draw a comparison. Imagine for a moment that you're in a movie theater, and as you watch the movie, your brain is retaining snippets of audio, little bits of visual data, probably the context, like who you're with and the smells and more, and is recording the key elements of the plot, along with anything else that seems of key importance to you. But your brain isn't recording a video of the movie into your head. You can't play it back word for word and scene for scene. Your memory operates more on impressions and on meanings. You remember the exciting and the emotionally charged parts, and you remember them in summaries. When you go to talk to your friends after the movie, you can discuss a lot, but you might remember different things or remember them differently. AI also works in impressions, much like you do, but with maybe a little less judgment and less filtering and quite a lot less context. So when AI looks at some input stream and reduces it down to its meanings, that's the making of an inference. And that inference represents everything the model understood about what it just saw. It might understand the themes of some text or the subjects of a photo. An inference might answer a question about these things or produce an embedding capturing all of the insights that it had. And if you only remember one thing from this talk, here's what I want that to be. Any input to a neural network that produces embeddings should be considered equivalent to the original inputs. That is, the vector embedding can be used to recreate the inputs. The AI can tell you all about a document, theme for theme and section for section. It just has to use its own words. Or it can approximately recreate images, plots, voices, faces, or whatever it's captured. Newer large models can extract quite a lot of information and understanding out of their inputs and can use that understanding in a huge number of ways. All right, so that should give you some basic understanding of what we're talking about and what embeddings are at a high level. We'll stay at the high level for now and move on to what they're used for so you can better understand the point. And in short, they have a lot of uses. In fact, many problems that were previously solved with custom-built models can now be solved better with generic models combined with memory and good prompts. We'll look at 3 of these use cases in depth, and we'll mention some of the other use cases after that before we move on to a discussion of privacy and security. So let's start with facial recognition. A model is trained generically on how to pick faces out of a photo, and then on how to understand the differences between faces, such as the relative distances between eyes and mouth and other features that allow us to tell people apart. The memory part is where those facial features are output as embeddings, one per detected face. So if we take a photo like this and run it by this special type of model, it can pick out each face and send a snapshot of each one onto its memory. Now that snapshot at a low level is stored as a vector or an array of numbers, which is what an embedding actually is under the hood. You only need to know this representation so you can understand what we do with them. But from a high-level view, this doesn't differ terribly from any machine-level representation of data, right? It all goes down to zeros and ones after all. But the important thing here is that given one face, one vector, we can find similar faces. That's because vectors have interesting mathematical properties. If we consider a simple 3-dimensional vector, we can plot it on a graph. We basically connect a line from the origin to the described points in 3D space, and then we can visually compare them. You can see which ones are more similar and which ones are more different. A vector representing a particular face can scan a vector database to find all other photos where that same face or one very similar to it occurs. Similar faces result in similar vectors, which cluster together. And as an aside, this graph was generated for me by ChatGPT with the Wolfram Alpha plugin, which is kind of neat. Okay, so vectors that are near each other in vector space or are similar to each other for some definition of similar can be used for clustering, finding groups of similar things, and for searching by doing nearest neighbor searches. And that's one of the core reasons for vector databases to exist. Their primary operation is this nearest neighbor search. But they can also be used for finding groups and predicting sequences. They're tuned to work well with lots of high-dimension vectors. And of course, they hold an awful lot of potentially sensitive data, such as vectors that identify people's faces. The second use case I want to talk about is semantic search. It's showing up under lots of names lately, like neural search, AI search, natural language search, and so on. Microsoft calls it cognitive search. The branding's kind of out of control. But the key here is an attempt to understand the meaning of a search to find more relevant results. So if we search for who is Barack Obama's wife in a classic keyword search engine, like this example on wikipedia.org, we get back the pages that most use the words in our query, all of which are actually about the former president. But if we use a search engine like Kaggle or Google that has a semantic engine, the intent of the words can result in much better results. And it doesn't just help with that style of query. There are a lot of words that have many meanings to them. So take the various forms of the word arms. There's a big difference between the political arm of some group, our bodily appendages, arming ourselves with knowledge, a call to arms, a strong arming someone. But keyword search engines don't understand context, and so all of these are effectively equivalent to them. But with semantic search, we can understand if we're talking about how to build strong arms versus how to strong arm. And so if we search on how to build strong arms, we might get back weightlifting exercises. And if we search on how to strong arm someone, we might get back something on mafia pressure tactics. Now, semantic search can be implemented in numerous different ways. Google has long used techniques with ontologies, but the new large language models like OpenAI's GPT-4 are amazing at this, and it's easy to use them to implement semantic search. It works like this. The input document is, if it's text anyway, is split up by chunks, for example, into sentences. And often these are partly overlapping to bring more context to each chunk. Each of those chunks are run through a large language model like GPT-4, which can be tasked with guessing what's next, or can be asked simply to remember what it sees, which is what we're doing here. In that case, it produces embeddings. Just like with the faces, these embeddings are vectors that are sent to a vector database for later use. So finally, when there's a query, it works much the same way. The model produces an embedding that represents the query, but instead of storing that embedding, it's used for a nearest neighbor search to find the snippets of documents that are most relevant to the question. Usually there's some kind of reference back from the embeddings to the idea of the source document for lookup, but also you could run it through generative AI to summarize the results. And this nicely sets up the third major use case, which is in fixing hallucinations. So these generative AI chatbots are utterly confident in their answers, but they're also bald-faced liars. They're just wired to write something that's plausible, not accurate. And they may be trained on information that's false. So to prove this point, we asked several open source models what Iron Core Labs does. But the responses were pretty laughable. They all guessed we were some kind of tech company, but one said we were a blockchain company, another said we were a healthcare company doing medical research, another that we were a services company doing dev for hire and consulting, and a fourth that we do AI research into computer vision. None of those are right. We're a cybersecurity company with data protection platform for cloud applications. But each of these answers was delivered with absolute certainty and a lot of backing details that were all just completely imagined. Now, this is a pretty benign example, but there are a lot of examples that are far less benign and that can damage reputations. AIs can be tricked into answering all kinds of unethical questions on topics like bomb making and crime, and they can display racist behavior and much worse. Some approaches to this problem try to detect bad requests and responses and just stop them, but that's a cat and mouse game that's far from being, that's so far being dominated by the prompt hackers. So the answer that seems to have the most traction today in terms of how to deal with this is to ask the AI to give its answers based on some specific context and to use that as its source material and to be able to cite its sources. You could feed it a huge amount of data as the context, but no matter how you approach it, you can't do this by using the model alone. This is sometimes called retrieval augmented generation or RAG workflow, and sometimes called grounding of an AI model. Which brings us back to those embeddings. Embeddings can be fed into models as context, and they often are. It's how a chatbot remembers what was previously asked, but it can also be a way to seed it with data, such as the data that results from a semantic search of a question over a database of known truthful answers. In Iron Core's case, we might send it embeddings that capture meaning from our website and then ask the AI to answer the question about Iron Core Labs based on that context, and then you'd be sure to get a reasonable result. So you select out some memory, which can be filtered in many ways. You combine that context with the question. The resulting answer is a summary of the relevant information that was held in its memory, or it's the actual results that the original document. And this approach to making AIs smarter, more truthful, and less likely to say things that will hurt people is quickly becoming one of the biggest use cases for embeddings. But that isn't all you can do with these. Many of the machine learning use cases that used to require custom models can now be managed with generic models combined with context from embeddings. So zero-shot recommendation and prediction engines, voice recognition, translations, image search over images or by a query that is itself an image, and much more. You can use embeddings as inputs to generative AI to get summaries or reproduce data. And the inputs don't have to be text or image, but can be almost anything from locations to purchase histories to videos. So let's talk about abuse. What happens if a hacker gets a hold of this embedding data, this AI memory? Well, think of it this way. Before, when hackers got access to data, they might have to go through tons of files or query SQL databases and search and sift and painstakingly hunt for the good stuff that they could use for their purposes. And that's not that easy. Now, the AI memory has its understanding of all the data that it's seen and stored as embeddings. Now, an attacker who gets their hands on this database can query it in natural language. They can surface the good stuff or summarize it or whatever. They can ask what confidential plans it knows about, ask about customers, executives, employees, medical problems, right? Whatever. Using vector searches and generative AI will make the hacker's job so much easier. It's like push button easy. It's trivial. They still have to get in, of course, but the vector database is a gold mine of data. Anything valuable in it can be easily uncovered. Are the upcoming quarterly results for Q3 going to meet, exceed, or miss expectations? The hacker might want to ask of a public company with some private data. But it isn't just the vectors themselves, because most vector databases hold the embeddings that are meaningful to the AI, but for each embedding, they can also have metadata, which can be anything. This is often needed to pre-filter data, for example, if you only want to search embeddings related to a particular user or company or age range or whatever. It can also save extra database lookups in other databases to deliver results back more quickly. But this data could be innocuous, or it could be highly private and confidential. It's just another place to put sensitive data that security organizations need to understand and manage. Now, before we get into the question of how to secure all that goodness in those vector databases, let's just zoom out for a minute, because this is really just one piece of a bigger puzzle. And consider that half of AI projects don't make it to production because of security and privacy concerns. That's huge. Most of what's being done is throw away proof of concept toy stuff because of these privacy problems. Just a few days of headlines shows a ton of these issues. Google didn't launch its chatbot Bard in the EU because of privacy. The US and EU are both aggressively pushing privacy legislation. Meta's Threads didn't launch in the EU. Google warned its own staff not to use their own chatbot. There are a lot of legitimate concerns right now, but importantly, if you build the system right, with privacy baked in from the start, you're just not going to have these problems. You'll be ready for legislation. You'll have your sensitive data or your customers' sensitive data under lock and key. And the sooner you can use this tech, the sooner you can reap the advantages of it in terms of efficiency and power and business value. If your competitors are using the tech first, will be hamstrung. But if you can use the tech safely, securely, and privately, you can win and win again and keep on winning. Now, there's an entire landscape full of security threats and solutions to them surrounding these AI systems that are trying to address all these emerging problems. I have a YouTube video that I recommend you watch if you want a breakdown showing example companies and types of solutions in these spaces. And you can find it by going to our channel page shown up here on the screen. But let me give you an idea now of what the categories are. From a high level, we have the process of building and training the model, which uses training data, which may be private and confidential. We have byproducts of applying data inputs, which may get stored in vector databases, and we have the point where users interact with these systems, usually in the form of querying them, although these systems may not be used directly by users at all, but queries may be made instead by machines to display recommendations or whatever. It's a hard system to capture simply and comprehensively, but this will suffice for the moment. So first, we have a class of products whose job it is to scrub and clean or lock down and keep private or inspect and report on the training sets so that the model is clean and can meet privacy and security policies and regulations. Second, we have a class of products that tests and audits models to make sure they aren't susceptible to known attacks and that they don't leak secret information. Now, some of these products also produce reports for various governance reasons. Third, we have model privacy products, which include ways to secure the queries going in, to secure the model itself, and to secure the inferences that come back out of the models. This category is the solution to the problem of sending all your sensitive data to OpenAI or whomever, right? Because it can make the holder of the model blind to the inputs and the outputs. Fourth, we have one of the categories with the most solutions available that we've seen at least, and some of these call themselves AI firewalls. And they monitor queries and results of queries going to and from models in an attempt to detect abuse of a model. attempts to steal the model, to evade safety protocols, and things like that. The fifth one is a new category we just stumbled upon since posting the AI landscape video, with only one solution so far that we've seen that can scan vector databases for sensitive data. Basically, you set up queries to search for health data or personal information of various kinds, and then you see if anything gets returned. The solution we saw doesn't currently deal with metadata, but it's easy enough to imagine this category working as a governance tool to help DPOs understand what might be held in their vector databases. And finally, the one we should put first, but we put last to help our next segue, memory privacy, which protects those embeddings in vector databases or wherever they live to reduce the risks around that data. And this is the one I'm going to go into detail on here in just a minute. The full landscape of solutions does seem like a lot, and it is, but in this age of large shared models, these general purpose artificial general intelligence models, the realm of things you need to worry about shrinks a lot. Instead of reactive solutions, you can focus on the proactive ones, which is why I recommend that most people focus on model privacy, or privacy from the company holding and running the model, and the memory privacy to protect the queries and inferences. This is the core of the system, and this is what you want to get right from the start. Building the model used to be 90% of the project. Now, 90% of the project is around how you use the model, which is why this makes so much sense. Okay, so let's talk about vector databases. A couple of years ago, these were very niche and pretty rare. Now it seems like they're popping up like mushrooms in a dark forest. There's been well over 100 million poured into these dedicated vector databases by VCs this year alone across a range of startups and open source spinouts. But search services and other databases are adding vector features too, making the range of available options quite wide indeed. When picking one of these, there are quite a few factors to consider: speed, scalability, types of operations you need to support for your specific need, ease of use, learning and adoption, cost, and how it's deployed. When it comes to deployment, you have a number of options. You can use a database as a service approach from one of the dedicated providers. This is probably the fastest way to get going, and you don't need a lot of internal expertise on how to tune these systems, which can be quite complicated, and you don't need to deal with all the many concerns surrounding them, which can add to costs and maintenance. Or if you're suspicious of third parties holding your data, but have made your peace with Amazon or Google or Microsoft or whomever, you can host yourself, but in the cloud on their infrastructure, possibly even with a service they offer that's semi-managed like OpenSearch and Amazon. Or you can own and manage everything and deal with the complexity and expertise shortfalls that come with that. So the fully hosted approach is best for privacy and for handling of private data. The on-prem approach is best for privacy and for handling private data, but the fully hosted approach is the best for getting going quickly, cheaply, and without a ton of expertise and extra time and cost. But in any case, if you can encrypt your data before it gets stored, it changes the entire equation when evaluating these options. Suddenly, the privacy and security story is as good as on-prem, or even better if it isn't encrypted there. Wherever you choose to host, privacy and security no longer need hold you back. It opens up a lot of solutions and saves money and time. So in a standard flow, where some input goes through some model and produces an embedding that gets stored in a vector database, you could have 3 different infrastructures hosted, potentially at least, by different people. So you might have your infrastructure in AWS. You might use OpenAI for getting embeddings, and you might store those embeddings in Pinecone, which then spreads and multiplies the risks to your data. But if you have some alternatives where you can actually run models in trusted computing or in fully homomorphic encryption ways using one of the companies who specialize in that case, the model provider doesn't see your inputs or the inferences in plain text, so they're encrypted for that whole part of the flow. And then once you get the embeddings, you encrypt them before sending them on to the vector database, wherever that lives. Which might beg the question, if the data is encrypted, how can you use the vector database for nearest neighbor searches, or really for anything at all? Generally speaking, encrypting data renders it useless until you decrypt it with a key, right? Well, yes, usually. But that's where property preserving data in use encryption comes in. This allows the data to be encrypted and to still be usable without decrypting it. Now let me define those terms. Data in use encryption is a fancy way of saying that the data stays encrypted even in memory. The computer processing and holding the data doesn't have the key or have access to the key, so that computer can be totally untrusted. And property preserving encryption means that some structure is preserved so that certain types of property checks can happen over the encrypted data to the database or whatever. It may as well not be encrypted, though the data isn't accurate and meaningful without a decryption key. Let's look at a quick example of one type of property preserving encryption that's fairly basic to give you some intuition here. Regular encryption is generally probabilistic, which means that if you encrypt the same thing 3 different times, you get 3 different ciphertexts. This is important so someone can't tell if the inputs are equal. But there are cases when you want to decrease the security a tiny bit, specifically so you can know if something is equal without otherwise compromising the inputs. And that's where deterministic encryption comes into play. Every time you encrypt the same input with the same key, in this case, you get the same ciphertext. If the input were an email address, you'd be able to look somewhat up by their email if you could first use the key to transform their email into its encrypted form. Then any database could do an exact match on it, and you can find what you're looking for. This means the supported property here is equality, and it's a form of property preserving encryption. You can't figure out the original email without the key, but you can figure out which emails are the same. All right, so with those concepts in mind, let's look more practically at how we can protect that AI memory, those embeddings, in practice. So we take a vector embedding and its metadata, and we retrieve a relevant key, and we pass those 2 things to an encrypt function, which returns an encrypted embedding and encrypted metadata. In that encrypted form, it's meaningless, and there's no harm and no breach disclosure triggered if that encrypted data is stolen, so long as the key remains safe. And since we talked about probabilistic versus deterministic a minute ago, it's worth noting that these encrypted embeddings are probabilistically encrypted. So if we encrypt the same data twice, we'll have 2 different vectors come out as a result, which strengthens security. But the resulting vectors remain neighbors in a different vector space. And if you've worked with encryption before, there's a random element per encryption called an IV that's returned on encrypt and needs to be kept if you want to be able to decrypt later. So with the Iron Core solution, all of the standard vector database operations, cosine similarity, Euclidean distance, dot product similarity, nearest neighbor and approximate nearest neighbor searches can work if you can encrypt the query properly before sending it to the database. If you don't have the right key, you don't get meaningful results. The encrypted query matches the encrypted embeddings, but if you don't have that key, you can't find neighbors, you can't use the data for generative AI, and you can't map the embeddings back to inputs. You can't otherwise search or leverage the data. And most importantly, if the data is stolen or transmitted to another country, it isn't considered a breach or an international transfer if the key doesn't go along with it. So in practice, you use Iron Core's cloaked AI to do the encrypting. This may be a proxy or an SDK, but either way, when you're saving data to the database, you take the embedding and the proper key, you encrypt it, and then you store it. In systems like these, the concerns around managing the encryption, the keys, the audit trails, the permissions, the security guarantees, all that stuff are often ignored. But we also have products that integrate with cloaked AI that help with exactly these issues and support important patterns for data privacy, like multi-tenant bring your own key and regional keys for data sovereignty and more. And importantly, these are optimized to be extremely fast. On the query side, it looks much the same. The query gets turned into an embedding, then passed to cloaked AI, which encrypts it before the query goes to the vector database. It's worth noting that cloaked AI has negligible performance impact relative to the network calls. And then, once queried with the encrypted query, the database provides encrypted results, and cloaked AI once again is needed to decrypt those results. In the process, the machine hosting the database and any of its admins learn nothing meaningful about what was queried and returned, and they know nothing about what's being held. But they can still do their job just as well as before. So in terms of deployment, Cloaked AI is deployed as a local Docker container in your infrastructure with a REST interface and an SDK to make calling it easier. Some languages, like Rust, do support in-process libraries for the whole thing. So the flow goes like this. Data is ingested by your AI app, then sent to the model, which converts the input to embeddings, which then go to Cloaked AI to be encrypted and finally get stored securely in the vector database. And that's it. It's dead simple to implement. Massively increases security while also freeing up a plethora of choices for where to store data and what stacks you can use. The memory of AI, the embeddings, are incredibly useful for a range of problems, from facial recognition to understanding search intent to stopping hallucinations. Vector embeddings, like human memories, capture the essence of the inputs and as such are just as sensitive as the inputs. And this makes them a new treasure trove of information and one that's easier to query and extract sensitive information from than other sources. When it comes to privacy and security in AI, there are some 6 different categories of solutions tackling a number of aspects of the problem. But the essential categories to pay attention to, particularly if you're using large shared models, are the model privacy and the memory privacy, 2 places where you can apply security proactively instead of reactively. Fifth, while AI capabilities have been leaping forward of late, it's useful to keep things in perspective and to see that human intelligence is, in most ways, far more capable than AI systems. They're game-changing systems, but they're not coming to get us. And finally, regulation is coming. In the EU and in the US, there will be privacy laws passed around AI. The media attention and the pundits mostly focus on the models, how they were trained, and on whose work and such. But when it comes to privacy, the private data is all moving into the vector databases. That's the new frontier for privacy. And cloaked AI solves these memory privacy problems. And with that, I'm out of time and out of slides. So thank you for coming and listening, and I'd love to hear the questions and answer as much as I can.
Awesome. All right. So everyone, hopefully you saw a little pop-up at the bottom. We do have a poll. If anyone is using currently a vector database, which one are you using? There are a lot. Patrick had a slide that had 10 or 15 different logos, and more vector databases are popping up every day. So go ahead and thank you. Yeah, all the vector databases. So yeah, go and vote on which one you're using. And we are about to head into Q&A. So it looks like we have one question already, but at the bottom of your screen, there is an Ask a Button question. Feel free to post your question there or in the comment section on the side. And we're gonna go through those and Patrick will answer. So the first one we have is, if you want to go, Patrick, to the section where you have the different vector databases and whether it's hosted and how private they are, or I believe this question relates to that. So Tugberg said, in one of the previous slides, how come choosing host is the most private version versus, yes, that one, fully hosted or hosted. Can you elaborate on that?
Generally speaking, a lot of the privacy regulations, a lot of internal policies have to do with who can see the data. And most companies feel like if only their own people can see the data, it's okay. And that's private enough. That leads to a lot of building on-prem solutions, meaning on-prem means like on your own computers and your own, data centers. On-prem is typically seen as being a private option for dealing with private data. Now, in my view, you should still be encrypting it and dealing with it as if it were, it could accidentally be made public in some time. But just the same, that tends to get a quicker pass. There's not a lot of paperwork. You don't have to do a ton of scrutiny on a third-party partner to see how good their security is and so forth. When you go to something like infrastructure as a service, like the Amazons and Microsofts of the world, or to fully hosted like the SaaS, options like database as a service type stuff, then you have to trust whoever's holding your data, because they might be able to peek at it. They might be able to see it. Who knows? You might be worried about subpoenas from foreign governments going to them and giving them, those governments your data, right? Especially if you're dealing with GDPR and international transfer issues. So when it comes to fully hosted, you can get tangled up in a lot of thorny security and privacy issues, which is why I say that generally speaking, on-prem is considered more private. It certainly gets a pass on that for most companies. But if you encrypt the data, then it really does change that equation. Like if it's going to be encrypted, first of all, especially if the SaaS company or the hosting company doesn't have access to the key or can't gain access to the key fully, then it totally changes the equation here in terms of what happens in terms of who can access it and what's available to a company that has those types of policies.
And Harjeet had a follow-up question of whether this can be achieved, the security you're talking about can be achieved through confidential computing solutions or confidential containers?
Yeah, absolutely. So I mean, in terms of what I've seen for confidential computing solutions, that's what I call the model privacy area. So strongly recommend confidential compute as an approach to dealing with model privacy hosted by others. That doesn't really deal with the vector database aspect. I suppose you could run a vector database inside confidential compute where its files are encrypted before being stored to disk. I haven't seen anyone doing that specifically. This is a way to not have to have confidential compute wrapped around your vector database. And so that's where we call out memory privacy as something different. But yeah, confidential compute is very much like one of the two main approaches that we see to the model privacy side of things. It's either confidential compute or fully homomorphic encryption are kind of the two categories there.
Awesome. Thank you. So Joe also asked a question. One of the things that you talked about is performance, and how near the end of the presentation where you were talking about Cloaked AI, which is our latest offering where you can encrypt the vector embeddings and secure those. So how does that Cloaked AI and in the encryption impact performance for people who are using it to protect the vector embeddings?
Yeah, I mean, the actual encryption is smoking fast. It's negligible in terms of the time it takes to deal with your data, in terms of what it's going to take. But that does come with an asterisk. If the encryption key has to be fetched, or you have to call out to some third-party service every time to get the key or something like that, it could slow it down. So it really does depend on the key management strategies you use to some extent. The actual encrypt and decrypt, smoking fast. So performance, if we mean performance in the sense of speed, which you do in this question, yeah, it should be negligible compared to other network calls you're making.
Awesome. All right, let's see. Any other questions? I know one of the things that we often get asked, and I think I'll just go ahead and bring it up, is there are a lot of assumptions about encryption that encryption in transit is adequate. And that's something we typically get asked because a lot of these databases will say, well, we encrypt in transit and at rest. That's good enough. It checks that encryption box. Can you talk to why that's not actually a legitimate solution?
Yeah, if I was a little smarter, I would have put something in my appendix ready for this, because it is a common thing that we hear. People say, "Oh yeah, we encrypt, at rest and in transit." And what they mean by that is that they're using HTTPS for requests, and that somewhere low level on a disk, things are encrypted. Typically, that's a transparent disk or database encryption or infrastructure level encryption. And it doesn't actually protect the data from the types of threats we're talking about. So the in transit, I mean, these are still both very important things to do, don't get me wrong, but they are not checking the box on the data protection. So that at rest encryption, it doesn't do anything on a running server. And these servers are running 24/7. It's effectively invisible encryption even to attackers in that scenario. Excuse me. So it's not data protection until someone pulls the hard drive out of the computer and then throws it in the dumpster and back. Well, then someone who tries to use the hard drive is going to find that the data is all scrambled, which is great and important so people can throw away hard drives. But for data protection, for data privacy, for dealing with things like, especially if we're trying to think about, hey, do we want these admins to be able to see our data, or subpoenas to be able to get access to the data, or what happens if a hacker gets into this infrastructure? How bad is the damage to us? How sensitive is that data? How much risk to our reputation, to regulatory infractions and so forth do we have? Then you need a different level of data, which is what we call application layer encryption, which is just a fancy way of saying, encrypt it before you send it to the data store so that it's totally opaque if someone gets access to the data store. So if you're an S3 bucket that's accidentally made public, or a database that has some SQL injection attack that's susceptible to, or whatever, not the database, but the application is, then in those cases, the data that comes pouring out is totally opaque and useless to any attacker.
That's great. Yeah. So anytime you have a vector database or another database claiming encryption, Ask them about application layer encryption. Do they offer that? That is a great way to determine what their how advanced their security is. So we have some other questions here. Colt is asking, have you done testing on precision and recall for encrypted versus plain text embeddings for nearest neighbor search? This also going back to our cloaked AI product.
Yeah, so when people talk about embeddings, and actually a lot in this AI, especially large language model world, they talk about performance in not in terms of the speed of something, but in terms of like how well it does on certain tasks. And these things can be impacted by different things, including encrypting, but also by using approximate nearest neighbor searches instead of nearest neighbor searches, and so on and so forth. Basically, it's something on the order of 5 to 10% decrease at the lowest recommended security setting. That would mean, so if there were scores in the, let's say, of a performance score for an embedding retrieval in the 55 range, it might drop down to a 52 or a 50 or something like that. So it does have some impact. It's fairly low, and it is tunable. So you can set your security level, if you're familiar with encryption, at the lowest end at around 100 bits, or you can crank it up if you're able to tolerate slightly, depending on what your tolerance is, depending on your use case. So I'd say it's pretty good and pretty minimal.
And I think this question might also have been partially answered by what you just said of, what about performance in context of search results? So when you're encrypting and using cloaked AI, does that impact the information that you're getting back?
So generally not. There's a very slight error rate that comes in that things are kind of fudged around. So neighbors, it may not be exactly the same order. In our testing, it comes out with basically the same results, sometimes not in exactly the same order. So the we'll be publishing a whole bunch of data on this, and we'll also be publishing source repositories so people can run their own tests. We've been running them against the standard benchmarks in this space for data sets and so forth to understand how they perform. But of course, people are welcome to test it on their own. I think the important takeaway, though, is that for most people, this won't be noticeable in terms of the results. You can encrypt it, and you can get back equally good results.
Great. Well, and I posted a link to the Cloaked AI page. So if this is something that interests you, if you're building an AI product right now and you are concerned about privacy and security and how you're going to communicate that to the users of your product, we have a waitlist that is open. So if you go to that link that's right up here, you can join our waitlist and you will be an early beta tester. And we would love to have more beta testers join us. And thank you everyone for joining us. Thank you, Patrick, for a great presentation. Everyone here, you will also get a recording of this, and we'll be sending out Patrick's slides so that you can get a PDF of that as well. So thank you, everyone.
Thanks very much. Appreciate you being here.